Now that we got all the distribution of the moments, now we are going to check for one particular instance whether whatever the demand that we have got and whatever the reinforcement that we have, cable profile that we have given, whether it is satisfying the capacity limits or not, right. So, let us look at it. Factored moment at mid span, for example, when I look at it at east west span, it works out to be 621.7 kilonewton meter, and area of the pre-stressing steel that is crossing this section is 3059.7 millimeter square. So, depending upon the number of cables that what we have, right. So, this is a uniformly distributed span. Then initial strain, as you can see, is 110 is a effective pre-stressing force that you divide by area of one cable multiplied by the elastic modulus will give me the strain, right. The force divided by area will give me stress, stress divided by elastic modulus will give me the initial strain. Then we are applying the equations of equilibrium. Compressive force in the concrete has to balance the tension force. So, 0.36 FCKB x cube, this is this, and strain in the pre-stressing steel is by using strain compatibility. We have studied in the Flexural chapter, and ultimate strain epsilon Cu is taken as 0.0035, and we can calculate your strain in the level of pre-stressing steel, assuming your strain linear strain variation. This is your epsilon Pi, right. So, this plus the extra strain that it is due to the external load, that is the total strain. Let us assume that the pre-stressing steel is going to be yielding. So, we can take this and multiply this to get your tension force, right. So, if you do that, satisfy C is equal to your T, which we have already found out that. So, then we can get your x neutral axis depth is 37.87 millimeter and your strain is 0.0211. So, definitely it has yielded. So, our assumption is correct, right. So, these are your from strain diagram that we have done. So, you can go back and check your Flexural chapter how you calculate your strain, and this is your area, right. So, this is your area and this is basically nothing but your stress Fp. Fp into Ap will give you your tension force, right. So, this Fp again is coming from your stress strain diagram. So, you have assumed a bilinear curve if you remember previously. So, you can go back and check, and this way we get your stress multiplied by the area of pre-stressing steel will give me the tension force. So, we get all these things. So, by satisfying the equilibrium, then we get your neutral axis, from that I can get your exact strain, and we have verified that it is yielding. So, tension force is this. So, the moment resistance is going to be T into D minus 0.42 XU. If you substitute, you get your resistance as 928 kilonewton meter for this section, and my demand is only this much. So, basically my capacity is higher than the demand. So, we can check for other sections as well, right. So, this is for flexure. So, we have done the initial design, we have checked everything, flexure it is okay. Now, how about shear, right. So, shear is where now again we have told you we have to be careful, especially for a flat plate, right. So, again from this bending moment diagram, we need to find out where the shear will be maximum, right. So, basically we can find that x will be 3.42 meter from the A. So, the moment at any section between A and B, we can write this. Now that you know the distribution of your n moments and you know the load that it is acting, the external load that it is coming. So, from your free body diagram, you can find out the simplified expression for the variation of a moment in any span between, for example, between A and B. We find this as negative 840 plus 183.6 divided by 8, because the span is 8 times x. Then this is a reaction due to your external moments, the fixed the support moments. Then you can plug in this to get your distance at x is equal to 3.42 meter. Basically your moment is becoming 0. So, you get that. Now, for the similarly for east-west column at B, then we can find out that at moment section. So, similarly, the maximum moment locations can be found for other directions as well. So, these are all the locations for your maximum moment. Okay. So, that is what we have. So, this is basically 4.11. So, this is where your maximum moment is. So, these are basically first derivative we are equating to 0 to find out where the maximum moments are going to be. So, this from structural analysis, once you find your support moments, you can invoke your free body diagram and find out where the maximum moments are going to be, and at any distance x you can find out what is the moment acting at that particular section. So, we found out all those things. Now, we have to check the shear capacity. So, now let us take effective depth as 200 millimeter for the slab. Now, the direct, so as you can see, in this for the punching shear, you will have two components that will be coming. One is the direct shear component, which is nothing but Wu, which is your factored load multiplied by the tributary area minus this area, the critical perimeter area, right. So, this is basically C1 plus D, right. So, whatever that the load around the perimeter, we are calculating now what is the shear at the perimeter location, right. So, that is the reason this is the total tributary area minus this C1 plus D that we have to take. So, you get your shear demand as 1297.9 kilonewton is only from direct shear. So, this is the total area, tributary area, right, and this is a factored load divided by the critical perimeter area, right. So, you get your factored direct shear. Now, for unbalanced moment, again we have to calculate your area of the cross section that is resisting that shear is critical perimeter 500 plus 500 plus 2 into 100, that again you multiply by twice and your effective depth. So, this is the critical shear perimeter area. Now, what is E1 and E2? Again we have calculated now. Similar to polar moment of inertia, sectional property has to be calculated to find out what is the shear distribution from unbalanced moment, right. So, E1 and E2 is here is 350 millimeter, and J1, J2 are your sectional properties, right. Now, I have 4 cross sections around that column is resisting this unbalanced moment through shear. So, I have to calculate this J1 and J2 parameter, as we have discussed it in the previous module. So, if you do that, you get your J parameters as 4.67 into 10 to the power of 10. Then gamma V factor, how much of this unbalanced moment is actually getting transferred as flexure and shear. That also we found out using the equation. This is a column dimension plus your effective depth. So, that works out to be 0.4. So, that means whatever that unbalanced joint moment is there, 40% of them will be transferred through shear, right. So, we can find that. So, now the moment must be calculated at, because now we have to calculate at 350 millimeter at the critical perimeter C on the either side of the B. So, this is the joint that we are looking at. Now, I have to calculate at a distance x is equal to 350 millimeter on the either side of the B, both on the left side and right side. So, moment equation is this. Now, moment at 8.65 meter is 756.74 kilonewton. Similarly, to the right side of the B, I am getting 610. So, these are the moment that are acting at that particular locations, right. So, we take that, right. So, similarly, we get these two moments for this calculations. This is for the east-west section. So, these are the unbalanced shear calculation on the either side of the column for the east-west. So, previous one is for the north-south and this one is for the east-west. So, we got this, what are the moment that are acting on the left side and right side, right. Now, the difference is basically nothing but your unbalanced moment, right. So, we got the unbalanced moment. Now, for the unbalanced moment, we have to somehow include it in both the directions. So, this is from direct shear. This is from unbalanced moment transferred through shear. Now, about the x axis and then about the y axis, right. So, Jc is your polar moment of inertia, sexual property similar to your polar moment of inertia. So, when you substitute all these values, you get your direct shear plus these are the unbalanced moments. So, this is your mu p in the x, I should say mu v in the y direction. So, these are the unbalanced moment that are being transferred through shear, and okay, this is your unbalanced moment, I should say. Anyway, the 0.4 factor is coming. Why? And this is your gamma v factor, right, and this is your perimeter C1, right, and this is your J parameter. So, if substitute all these things, you get your total shear stress is 2.61 megapascal. Now, what is the shear capacity? Again the same equation. So, we are going to use Ks into tau c plus 0.3 into Fpc plus Vp by P naught by D, and shear resistance due to vertical component of precessing must be determined by summation of the components of the tendons of both the direction, that we have discussed it in the preliminary calculations as well, right. So, there are 10 tendons in the north south direction banded, these are banded, and these are your uniformly distributed tendons within that perimeter B naught, only 3 are there. So, total 13 are there, right. So, now Vp is going to be this as per the profile. If you substitute that, I get 158.02 kilonewton, it is very close to what we had previously, right. So, similarly the average component in the north south direction, so when you put it, is going to be 5.87 megapascal, because I need to know what is the Fpc. So, now I am calculating what is the average compressive stress that is going to be there. Now, I have 10 cables are there. So, that is the reason this is your individual force Fp multiplied by number of cables, right, divided by the area. Area is now 750 multiplied by 250, right. So, 5.87, then you get average compressive in the east-west direction, only 3 cables in this region, so 1.76. So, we take average of these two as the Fpc. So, we take average as 3.82 megapascal. So, we substitute all these things, that you get your Vc as 3.01 megapascal, which is working out to be higher than the demand that what we got. So, for this particular section at this interior location, your punching shear seems to be okay, right. But having said that, you have to again further verify, especially in the now we have done only for this interior location. Now, the edge location and corner location, you will have even more critical parameters. So, that is the reason we have to be doing the calculations for those one edge location, one corner location also. Due to paucity of time, I am just showing one calculation for that interior location, but now that you got the moment distribution, from that we can, using the same process, now I can do the calculation for a corner column as well as for the edge column also. Now, we will quickly go through how we can do the same slab system using a commercially available software package, which is SAFE from CSI, which is a very popular software that is being commonly used for design of flat plate systems. So, let us create that, see the steps involved in creation of this, and then find out how these moment values that you calculated from your manual calculations are comparing with that of your commercially available package, right. So, first step, and this is a very simple geometry as you know, and we create all the columns which are all 500 by 500, which is routine, and you know how to create the geometry is very well given in CSI website. Some YouTube videos are there, you can look at it, how to create the geometry using this commercially available SAFE software. And again, height and below we are taking it as 3.35 and 3.35, and we have created the geometry, and then we also assume the design strips, and then here I can say in the north south direction I am assuming banded, in the east west direction I am taking it as uniform, right. So, we are considering this, right, and once you do all the analysis And we can ask in fact the software to calculate, if you give how much dead load has to be balanced, then software will automatically will give you what should be the number of cables in each design strip. And we have shown in manually, how do we get that, assuming 90% of the dead load has to be balanced. Here also you can give the the limits, and the software can tell you how much should be the number of cables, processing cable that are required. Now, for this particular example that what we have done, the software has taken and I gave at 90% the dead load has to be balanced, similar to what we did. So, the maximum camber work out to be 1.7 millimeter, and this is for only dead load and PT, right, and the deflection was 5.6 millimeter, right. So, the maximum deflection at some locations. So, you can see that upward camber is basically, you can see up to negative 0.666 millimeter that you have, right. Some locations you can see this is your. Now, when you have dead load plus PT final. So, PT final means including the losses. Obviously, the deflection has slightly become higher, and then the camber is also slightly reduced to 1.4 millimeter. Right. Now, this is for the dead load, live load and PT final. So, you can see that the maximum camber still is 0.75 millimeter and the deflection is 8.5 millimeter. And these are the strip moments that you can see at different locations. This is in the north-south direction, and of course, including 1.5 dead load and 1.5 live load. And you find that these are the strip moments in the north-south direction, and these are the strip moments in the east-west direction. Of course, here we also have the shear wall, that is, the effect is being considered, but in our analysis we did not really consider that. So, that is the reason you will find that the software will give you maybe slightly lower demand than our manual calculations, but our manual calculations are slightly conservative in nature because it is not really taking into account the stiffness that is coming from the core wall, which we have not really considered in our calculation. In addition to that, there is also corridor area that has slightly higher load, which you have not included in our manual calculations, right. So, now I think these are punching shear. So, you see that for this thing, several locations the punching shear is still failing. This is the punching shear values, right. This is for the factored load. So, you see that the flat slab thickness for 250 millimeter is actually not really satisfying the punching shear values at these locations. So, maybe what we have to do is we have to put a drop panel. Particularly in the edge columns and in the corner columns, these values you have to take it with a pinch of salt. They may not be exactly accurate depending upon how you create the geometry. So, in the edge columns like this, all of them, and in the corner columns, we have to be punching shear calculations. In fact, it is better to get the demand and then you use your Excel sheet or your MathCAD sheet to verify the punching shear distribution. So, and here also typically you will get higher values. So, then you can put a drop panel like this. Right. So, just to quickly show how the software values are being calculated, and punching shear particularly you have to be very careful, and you may end up providing some drop panel along with capital if required. Now, very important thing from bending point of view, you can see that what are the summary of comparisons between safe results and the manual calculation results. This is for one strip which is north-south direction. You can see that at end span at support I am getting negative 356 and the manual calculation is very close, nearly same. And mid span moment, if you look at it here, safe is giving you lower value and manual calculations are higher, and support also is always higher. So, at all other locations you see here, manual calculations are higher than what we get for your, but at the end spans we get nearly same values, right. So, you find that the comparison clearly shows that manual calculations are conservative, and for end moments of interior supports the manual calculations are approximately 20 to 25% greater than the software values. For mid span moments the manual calculations are approximately 30% greater than the software values for end spans. whereas for interior spans some locations it is higher. Again, that is because of the differences in the way that you have modeled and the way that we have done the simple calculations using your manual method. But having said that, it is always a good practice to have a Excel sheet developed for very common scenarios so that you can quickly check whatever the number that you are getting from your softwares is making sense or not. Otherwise, you can have very erroneous results depending upon the assumptions that you model and how you model it in a commercial package. You can always go back and check what are the number of cables that is the software is asking vis-a-vis what you are getting from your manual calculations. Very important for us to check. But still, the commercial packages, the punching shear calculation, there are some issues that need to be sorted out, and most of the design offices, what they do is for punching shear calculations, they take the demand from the software results and then manually check like what we have done. So that is the reason if you see our manual calculation for an interior span, it was working out to be okay, but in the software it was showing slightly a higher value. That is because of the differences in maybe in the number of cable that software it is giving, or in the loading that what we have considered, probably the corridor area higher loads that was more accurately considered in the commercial package than in our manual calculation. There could be some differences, but by and large you have to make sure that we are within that 15-20% of our expected results, then your analysis results and design results are correct. So, it is very important. Okay. So, now quickly let us summarize. In this part of the module, we have explained the preliminary design considerations for post-tension flat plate, and we illustrated the technique for designing the tendon profile using some simple manual calculations, right. And we went through detailed analysis of flat plate using equivalent frame method. Then finally, we compare the results of our manual calculations with finite element analysis, and we found that manual calculations in general are conservative than the finite element analysis, but not from punching shear point of view. In punching shear, you have to get the demand from software results, and typically you have to do the manual calculations, particularly the corner columns and the edge columns, where you may get erroneous results, and we need to be careful with that, right. So, with that we are completing this module. In the next part, we will get into some of the applications of post tensioning from strengthening point of view. Thank you.